in PRB. And we also have a supplementary work, which is a theory work published on the archive for people to look at. So a brief overview of what I'll talk about today will be a quick 20-minute talk. And so what I'll first introduce is how, like a quick primer on how we control our flux qubits, and then what type of noise we can expect our superconducting circuits to have, and then how we quantify the noise here at D-Wave Systems, and then I'll leave you with some final remarks. So at D-Wave Systems, we're focusing on improving the performance of our quantum annealing processors, and this means that we both want to increase our qubit count and our connectivity, but also at the same time reduce the amount of noise that our superconducting circuits are seeing. And this all has to be able to be facilitated in wafer scale fabrication, because that's the way that we fabricate our devices. And so what we really want to do is be able to probe the noise that's each one of our qubits is seeing in the fabric of our quantum annealing processor. And so that means that we have to use the same control lines that our annealing processors would use. And what we're tracking, a key metric, is our integrated low frequency flux noise. And that's what's being plotted here on the right-hand side. This is a tunneling line width on the y-axis, and I'll come back to what this metric actually is in this talk. But you can see our R&D efforts are proving to pay off, that we are lowering the amount of noise, our integrated low frequency flux noise that our qubits are seeing. So you can see that our consistent investment in our noise program is actually starting to pay off. And at D-Wave Systems, our main technology is using rf-SQUIDs. On the left-hand side here, you can see a schematic of what's called a compound Joseph junction rf-SQUID. What it comprises of is a superconducting loop, which allows for circulating current states. So these are our flux qubit states that are circulating around the loop of this superconducting loop. And then we have a small loop that interrupts this larger loop. And what this allows us to do is tune the critical current that's flowing in the body of this superconducting loop. And here what I'm plotting is the potential energy of this circuit, where we bias this superconducting loop to half a flux quantum. Now you can see there's a few different traces here with this parameter called beta. And beta is this parameter which is tunable by the flux that's in this smaller loop. And this allows us to both create and destroy this potential barrier between these two, what will become these two flux states. And so this allows us to in situ control the height of this double well potential. So with this double well potential, we can create something called a flux qubit. What's being plotted here is this in black is that double well potential again. And you can see that we have a ground state, this symmetric wave function, and this excited state, which is this anti-symmetric wave function. We can use these energy eigenstates to compose flux states, which are wave functions that are localized in each one of these left and right wells. And this will be our flux basis that we'll measure in. Different control knobs that this circuit will have. So in this schematic, which is similar to the one on the previous slide, we have two superconducting loops. Now in this major loop here, what we're able to do if we apply an external magnetic field to this loop here, we'll tilt the potential so that we can tune the energy alignment of one well compared to the other well. And so this is our energy bias. And then we have, with this smaller loop, what I introduced on the previous slide is we're able to control the height of this barrier, and this will tune the tunnel coupling between our two states. Now, since these are superconducting circuits, we have some different types of noise that we would expect that these circuits will see. One of the main ones is thermal noise. So this is going to be white noise. So it's frequency independent. And this is why we measure our devices in a dilution refrigerator such that we can get down to around 10 millikelvin to lower this amount of noise as much as possible. Another ubiquitous type of noise is 1/f noise. So this is a noise that's peaked at low frequencies and decays going to higher frequencies and typically has this 1/f type spectrum. And then another type of noise is called quantum Nyquist noise, which is actually linearly increasing with frequency. And so what we want to do at D-Wave Systems is look at different types of noise and see how they're affecting our qubits. And we want to be able to measure these different types of contributions, because currently we don't know exactly what's causing these, but we want to be able to lower them to be able to get a more performing processor. And to do that, we're tracking two main types of noise, one being flux noise. And this is because our qubits have superconducting loops. So there's going to be flux noise that couples into them. And then there's also charge noise. And so in flux noise, we're tracking three main metrics. We have low frequency flux noise, we have which is ranging from millihertz to kilohertz. We have our midband metric, which is this tunneling line width, which we're saying is our integrated low frequency flux noise and has a range from kilohertz to gigahertz. And then we have in broadband noise, which is this ohmic spectrum, which is linearly increasing with frequency. And this ranges up into the gigahertz. And so we're able to measure these different types of flux noise, but the focus on this talk was about how can we measure charge noise in these systems and how can we distinguish it from flux noise. And we're lumping this into a broadband spectrum, which has a range from kilohertz to gigahertz, and is associated with this commonly referred to dielectric loss tangent. Now you can see in this illustration on the left-hand side here that there's a difference between positive and negative, or the spectral densities at positive and negative frequencies. And this just means that it's associated with the qubit either being absorbing some energy from the environment or emitting to the environment. And in classical case, we'll expect that this actually just to be symmetric. So positive and negative frequencies are the same. But in the case of a quantum system, our noise operators don't need to commute. And so we can get this difference between the qubit being able to emit to the environment while the environment doesn't always have to excite the qubit. And so a brief disclaimer about what we're doing at D-Wave Systems. So what we're doing is probing these spectral densities, and we apply phenomenological models to try to understand what different noises are, or the different strengths of the different spectral densities that we can have. And we hope this will motivate a better understanding of the microscopic mechanisms, but these phenomenological models are not motivated by microscopic mechanisms, but we hope that by measuring the different strengths of, say, the ohmic noise or low frequency flux noise, we can get a better understanding of what's causing these noise sources. So one technique that we use to measure low frequency flux noise at D-Wave Systems is a measurement where we can actually measure what we call the qubit degeneracy point as a function of time. So in this upper plot here, what I'm showing is a transition where we're applying a bias to our qubits, or either localized strongly in the left well or the right well. That's going to be 0 or 1 on the scale. And if we're at a bias of 0, our two wells or two flux states are degenerate, and we get a population of around 50%. So we can track this 50% point as a function of time and create a time series. What this allows us to do is, if we take the Fourier transform of this time series, you get a spectrum that looks like this, and you can see that it's peaked at low frequencies and decays going up to higher frequencies until it reaches our thermal background or our white noise. And so this follows what is expected to be a 1/f type spectrum. You can see that it's peaked at low frequencies. We normally have amplitudes of around a few microphi per root hertz. And there's a parameter alpha, which is how 1/f like it is. And usually this is around 1. And this type of noise seems to be quite used. Most groups or labs around the world that measure superconducting circuits with loops see this type of noise. And there's a lot of ongoing research into understanding what is the actual cause of this. So you can say, okay, if we're able to measure this type of spectrum, why do we need to have any other measurement techniques? But you can see that the frequency range that this measurement is over is millihertz to hertz. So we're not able to probe up into those gigahertz regimes that I was showing on the previous slide. And what we want to be able to do is probe to those higher frequencies, but we want to still use our same control lines that we use for our quantum annealing processors, which have limited bandwidths. So we want to be able to use these control lines, but be able to measure up to higher frequencies. And that's where this measurement technique called MRT, or macroscopic resonant tunneling, comes along. And the idea with this technique is that we have a very high barrier between our two flux states, such that we have a small tunneling rate from one well to the other well. And what we want to do is measure this incoherent tunneling rate between the two wells. And this tunneling rate will be dominated by the noise that our system is seeing. And so we'll measure characteristic line shapes that will be broadened by the environmental noise that are seeing, and we can try to piece apart different sources of noise from our line shapes. And so this is what I'll be talking about today. I'll briefly introduce how we actually do this measurement technique first. So the technique revolves around first resetting our qubit. So we want to erase any flux that's in the qubit, and the way that we do that is just create a monostable potential. Then what we do is we bias the qubit such that we can start to force it to localize in one well, but still this is a monostable potential. And then we want to initialize the qubit in a known configuration. So what we do is then raise the barrier such that we have now defined a left well and a right well. But you can see from the strong bias, we're going to be biased in an initial well. Here in the schematic, it's the left well. And then we put the qubit into a known initial flux state. So this will be a bias that we want to measure our MRT at, while the barrier is still high, so no tunneling will occur. And then the MRT protocol, what it does is we lower the barrier to a target level such that we always get the same tunneling rate or tunneling amplitude. And then we dwell at this time, and depending on the certain conditions that we have, either we'll have tunneling or not. And what we want to do is then measure the probability of this particle tunneling as a function of how long we dwell for. And so that's what's shown here in this plot here is the population or probability of being in the initial well. And you can see for different amounts of dwell time, that's plotted on the y-axis or x-axis here, we start to escape out of the initial well. So depending on how long we dwell for. The different colors here are different initial biases that we have applied to the qubit. And so what we do is we bias the qubit to a different position, and then we measure the tunneling rate from the escape rate from the initial well. And so there was some theory work to understand what we could expect from this type of experiment, because it is a little bit of an involved, it's not a direct technique that I showed in the previous example. And so what we found was that if you initialize your qubit in one well, the tunneling rate from going into the other well, this is going to be dominated by the relaxation dynamics of this tunnel coupled system. And this is going to be related to the noise processes that are ongoing. And so this work back in 2008, what they were able to show was that if your noise spectrum was dominated by low frequency flux noise, then the tunneling line width that you would measure, so as a function of bias, would have this Gaussian broadening. So what you can expect to see is this tunneling rate. So this is gamma as a function of your bias, will have this Gaussian shape, but also it will be offset from zero bias by this parameter epsilon p. So the width of this tunneling process is our integrated low frequency flux noise. And this bias that goes away from this shift from zero energy is actually related to this asymmetric quantum noise that I mentioned on the previous slide. So, but in our experiments, this is purely a classical effect where what happens is your qubit has a monadic moment, it's spinning in one direction, and this polarizes the environment. And you have to overcome this energy such that to be able to allow it to tunnel. It has this quantum noise analog, but in our case, it's a purely classical effect. And another interesting fact is that you can look at the detailed balance of tunneling from one well to the other well, and using this relates these two tunneling processes, and this allows us to use the fluctuation dissipation theorem to relate our width to this offset, and they're related by the temperature that our fridge is at. And this actually relates these two symmetric and anti-symmetric or asymmetric noise spectrums. So both this quantum and classical spectrums by this temperature T. So briefly, what we did previously, so this is back in 2008, right after this theory paper came out, we set out to do this type of measurement at D-Wave. And what's being plotted here in this plot here is in blue is initializing the qubit in the left well, and then we start biasing the qubit so this is tilting that potential. And you can see that the tunneling rate seems to increase and then decrease. And so it seems that we are on resonance with the excited or the other well around this point here. But the reason why it's offset from zero is that indeed we have that asymmetry, or that the shift that was predicted by this Gaussian broadening. And you can also see that the dashed line here is a fit to this Gaussian model. And so it fits quite well. And so this seems that our qubits were indeed dominated by low frequency flux noise. And this was what was also studied was the temperature dependence of this width and this offset as a function. Yeah, this temperature dependence. And so what's being plotted in red here is the offset. And you can see as the temperature of the fridge was increased, this offset seems to go to 0. And this is because we're starting to use that fluctuation dissipation theorem, and it's just starting to create this offset back to 0, while the width has a very weak dependence on temperature. And so a few years later, D-Wave Systems was able to decrease the amount of noise that the qubits were seeing. And what was interesting was that then when we measured our MRT spectrums, we actually didn't really have a fully Gaussian model or the Gaussian model wasn't fully able to capture the tunneling dynamics that we were measuring. So in the dashed line here is just the Gaussian model. And you can see that we have this tail that extends to higher biases. And we didn't fully understand what this was at the time, but then it turns out that we hypothesized that this could be coming from a high frequency noise source, which would have an ohmic type noise. So it's increasing linearly with frequency, as I showed in that quantum Nyquist noise was increasing linearly. And this actually, if you use this model, it actually is able to capture this high frequency tail that we're measuring here. And so I'll give a brief introduction to how we actually what we can do at D-Wave Systems to distinguish these two different types of noise sources. So say if we have a low frequency noise and a high frequency noise source, what we do is we want to measure the tunneling rate as a function of bias. And we have this, what we call an envelope function. And this envelope function will be dominated by both the low frequency noise and the high frequency noise. And this envelope function comes from the perturbation theorem for calculating our tunneling dynamics. But what it actually is just a Fourier transform. And since we'll have a product of Fourier transforms, this is a convolution of our different noise sources. So we have two different individual envelope functions. One will be the envelope function for our low frequency flux noise, and the other one will be an envelope function for our high frequency flux noise. Now, with the width of one of these, or the broadening that we expect from one of these envelope functions goes to 0, what this will turn this into is just a delta function, and we'll just be studying one noise source with respect to, and based on this convolution integral. The high frequency flux noise, we parameterize it by this broadening gamma. And what I'm plotting here on the upper left-hand side is just an illustration of the different types of noise that we can see. So the different colors here, the red and the red, or the blue and the red, are different initializations, like you saw from the data on the previous slide. Now, what you can see is if the width or our low frequency flux noise is large, so the width is large, you can see we have this characteristic large broadening. But if you decrease this, the width also decreases. So this is showing the dependence on our low frequency noise and how we can disentangle that from our high frequency flux noise, which is being plotted here. So if we have very low high frequency flux noise, this is the parameter gamma here. These different traces are different low or high frequency flux noise. See if it's quite low, then we just have this Gaussian broadened line shape. But as this increases, this tail gets larger and larger. And so what we can do is fitting these tunneling line shapes, we can fit this type of line shape to get our Gaussian broadening. And then this tail is associated with our high frequency flux noise. So we can capture these two different types of noise with this convolution technique. And then we thought, okay, so that tells us about low frequency flux noise and high frequency flux noise, but what about charge noise? And so what we started studying was what happens if we actually don't just tunnel into the ground state of the right well, but if we start tunneling into the excited state. Now this process once we tunnel into the excited state, we'll relax back down to the ground state. And this process is dominated, or this is an intrawell relaxation. And since there's an uncertainty of either being in the excited state or the ground state, this will also have an additional broadening. And so we parameterize this by another envelope function, and we can just use this convolution technique to include it in our calculated measurement or calculated measurement rates. And this parameter gamma or zeta is parameterizing the broadening coming from this intrawell relaxation. And what's being plotted here on the left-hand side is our tunneling rates. And you can see this is for only tunneling from one well to the other well, and this is our going into our ground state. So this is that first peak. And then we have our second peak here. And the different colors here is this different broadening from our intrawell relaxation. And this, you can see, is once this is increasing, we start to increase the broadening in this valley here, but also that the higher peak gets this additional broadening based on this relaxation mechanism. Now we've looked at numerically what would we expect this process to be dominated by, and it looks like it's charge noise. So we can actually use this broadening to calculate our dielectric loss tangents. So this is the loss tangent associated with our charge noise relaxation in our qubits. And this is parameterized just by this value of the broadening divided by this peak spacing, if we assume that we have a harmonic oscillator. We use this harmonic oscillator or approximation for the rate well. And so what this allows us to do is use this, what we call multi-level MRT. So not just tunneling into the ground state, but also into this higher state to characterize the amount of charge noise that our qubits are seeing. And so what we did was we wanted to measure this effect. So first what we did was we cooled down our devices, and then we measured this zeroth order transition, or where we were measuring the first peaks. And that's what's shown in this inset here. We have this Gaussian broadened peak that has this high frequency tail. So we use this convolution technique to fit both of these. And we use that to set what our low frequency and high frequency flux noise are. And then what we do is we continue to measure as we increase the bias until we are aligned with the excited state. And you can see this is where we get this additional peak here. And then what we can see that when we tried to fit this this valley, if we didn't include any intrawell relaxation, we weren't able to describe this tunneling width. So what we had to do was actually fit this with our parameter zeta, and we're able to capture this intrawell relaxation. And we saw that this higher peak had an additional broadening that was not captured by our flux noise. And so what we can do is we can use this relaxation that we measured to estimate what the dielectric loss tangent was. And that's what's being plotted here on the left-hand side. We have a couple different dielectric loss tangents that we measured. This is a spread over 27 qubits that we measured. And the loss tangent we're getting out is around 10 to the minus 3, which is consistent with what we expect for silicon dioxide, or silicon oxide, which was the dielectric that we're using in this experiment. And from from our first order transitions that we're measuring, we can also estimate a parameter which we call our inductive loss tangent. So this is our parameterizes the inductive losses. And this we get around a few 10 to the minus 6 for inductive losses. And so we use this technique quite a bit at D-Wave Systems to be able to track what type of noise improvements our processors are seeing. And so on this slide, I'm just showing you our new processors, where they're called Advantage2. They're not, and this is ongoing work. But what you can see is we had a prototype Advantage2 processor, and here's this 1/f spectrum that I was showing you on way back at the beginning of the slide deck. And what we've seen that is we're able to, by improving the materials that we're using, we're able to see that we're able to lower the low frequency flux noise by a factor of 4. And what's being showed here on the right-hand side is our MRT tunneling line widths. And you can see that also our prototype and what we're working out with now, we've really decreased the amount of flux noise that these qubits are seeing. So we see this also this reduction of a factor of 4 of our integrated low frequency flux noise. And that leaves me with the summary of what I've talked about today. So what I've tried to introduce is how we actually are able to measure noise here at D-Wave Systems, and how we're able to use this convolution technique to be able to separate different noise contributions from our tunneling line widths, and that we're able to now be able to measure charge noise in these systems. And all of this is facilitated by our low frequency lines that we use for quantum annealing. And with that, I'd like to thank you for listening.
Okay, thank you very much. Very impressive talks. Actually, I'm really impressed by the experimental data of the distribution loss tangent distribution. It's quite important information for improving the coherence quantum annealing machine. So anyway, so now the session for the discussion of the comments. So if you have any question and comment, please switch on your microphone and the video. Yes, okay. Dai-san, yes. Please.
Yeah,
yes.
hello. Yeah, this is very impressive work. Yeah, I have a few questions. So my first question is, so actually, can you hear me well?
Yeah.
Okay. Yeah, so my first question is, are you able to characterize the charge noise over different generations of the devices? Like, do they improve? Like, yeah.
So since this is quite a new experimental technique, we can't go back and characterize what the charge noise was in previous devices because we weren't measuring this higher order MRT peak. So it's only something that we can do going forward. But we are using it to improve our devices and just understand the different materials that we have.
Right, cool. Yeah, and then my next question is, like, how do you think this charge noise can be used, like the measured charge noise strength can be used to model or explain annealing experiments? Or because I think you said this charge noise mainly comes in when you're tunneled to a higher excited state of the one well. Do you think in an annealing experiments, like, will with higher excited state play a role as well?
So it depends on what annealing schedule you're looking at. It definitely we have been focusing mostly on decreasing our low frequency flux noise because this is going to give us misspecification errors. But definitely, charge noise is going to also give us misspecification errors. It's just not as strongly coupled to our computational states that we use for annealing. How it'll affect? Yeah, we're not really, like, I know there's annealing protocols out there to use the excited states, these diabatic annealing schedules, but so definitely charge noise would affect those as well. But our typical annealing, what we're just seeing is that since we've been lowering our low frequency flux noise so much in our current generations, our charge noise is becoming one of the dominant noise sources that we're seeing in these tunneling experiments.
Right. Yeah, because I imagine when you are still kind of in the single well regime, this charge noise will affect your, like, relaxation and excitations.
Yeah, so it's also going to give, if you bias, say if there is some jiggle to your flux bias and you are slightly off degeneracy, this is, say if we have a specification of an H and we are biased, there is going to be some additional broadening coming from this intrawell relaxation. That's in the MRT rate, you saw that it starts ticking up. So it depends on which H that you've specified and how far biased you are from degeneracy.
Right. Yeah, thanks a lot.
Okay.
So I had a question as well.
Yes, okay. Of course, yes.
So
yes.
in the very first plot on your presentation, you had some tunneling width or something. Did you mean W or did you mean something else?
Do you want me to try to find that slide?
Yeah, if you can.
Was it this one here?
No, it was the very first slide, I think.
Oh, yes. This tunneling line width is indeed, yeah, our integrated low frequency flux noise. So this is our width of our Gaussian broadening.
I see. So I'm finding kind of it hard to compare these different generations because I suppose it's a dimensionful quantity, so possibly other parameters also have changed. So can you motivate this as a quantity that matters?
So what we're trying to, yeah, parameters do change, but this is our integrated low frequency flux noise. So yes, we do change our energy scales for different generations, but what we want to effectively do is just reduce the amount of low frequency flux noise these qubits are seeing, even if we have changed the parameters, say if you change the energy scales for our devices. So it could be like, there is one way you can decouple from noise, both by making better devices, or you can also improve your materials. And we're doing both of these things at D-Wave.
Right. But there's a naive way to improve this quantity by just making a smaller loop, right? So I'm just asking if you're not doing that. So the loop size stays the same.
I cannot comment on that.
Okay.
Okay, so any other question? So
May I?
question. Okay, Myoji, please.
I'm not familiar with the noises, so this is a very naive question. But you mentioned your model is phenomenological, but I'm not sure what point is phenomenological and which point is what we can derive from some microscopic model.
So there's definitely different, like there is a lot of work going out to try to understand what the microscopic models are. Some people say that for flux noise, that it's oxygen that's on the surface of your wiring layers, and those can have unpaired spins. And so you could make a model based on that and predict what the low frequency flux noise is. There's also models of that there's spin diffusion along your wires, and this can also give you low frequency flux noise. So there's clusters of spins. But what we were doing initially, this was kind of like a historical overview of how this MRT technique developed. And what it was just looking at what these tunneling line widths were, and say if you a priori just said we have a 1/f type of spectrum, not knowing what the microscopic model is, but if you had this type of spectral density, what would be the line shapes that you get out of that? And I think, there is a lot of work being done on understanding what the sources of low frequency flux noise is, but this ohmic, like high frequency flux noise, I don't think we have very good understanding at all of where that's coming from. So that's why it's very motivated by just phenomenological models. For charge noise, there's, all the literature that's revolving for transmons. There's a lot of work on understanding the fluctuations that you can get for charge noise. It can also have the similar types of spectrums that you can have TLSs, you can jump back and forth and you can get low frequency flux noises from those. And people are also seeing ohmic spectrums for charge noise as well. But yeah, and there's a lot of the interesting thing is with this 1/f type noise is that people see it in many labs, and it has usually around the same magnitude and the same type of exponent. So it seems that it's something intrinsic to superconducting circuits. And there's been a ton of research into trying to understand what the microscopic mechanisms are, because what we need, like if we actually understood what was causing it, then we know how to mitigate it.
Okay, thank you.
Yeah. Oh, so okay, it's almost time's up. So okay, so thank you very much for your really interesting talk, and actually I'm really impressed. So okay, so it's time to close today's INQA seminar. So I hope to see you again next week. Yes. Okay. So Alex, thank you very much. So okay, see you. Bye.
Thank you everyone for coming.
Yes, thank you for coming. Bye. See you.
Bye.